we are missing people. Oh, maybe not. All right, any second my notes will load. We'll get started. All right, so let's take attendance. And so just let me know if you have go by a different name or anything like that, or if I horribly butcher your name, please correct me as well. So Kylie, thank you. Joshua, thank you. Adara, thank you. And Adara, you are not registered for recitation, correct? You need to register. So that goes for everybody in here. So you have to be in lab lecture recitation. It's one giant 5-package course. If you don't take one, you will like essentially just screw yourself over for all eternity. So yes, please register. As soon as this loads, I'll write the code for you, and then you can join by permission code. Jonathan, missing Jonathan then. Emma, thank you. Terrence. And Alicia, missing 2 people. So no Jonathan and no Terrence. Okay, perfect. So yes, sign up ASAP. I'm looking at my roster, so it looks like just have one person missing. And what's your name?
Trey.
Does that make you Terrence?
Yep.
All right, so you go by Trey?
Yep.
Perfect. Thank you. So we're just missing Jonathan. So the recitation code is VTBM. So add that ASAP. You have to have all 3. And I think, Dari, you're the only one, not to call you out and pick on you, but I'm just looking at my rosters right now. All right, so my name is Marissa Shepard. And I have a PhD in chemistry. And so we'll be having a fun time in Chem 104. So this is just an introductory course. And so the best way to reach me is email. And so my email is mshepard, and shepherd is spelled like the sheep herder. And please don't misspell it. That is the most common issue I notice. People try to email me, and then they say, you never responded, and they misspelled my email. So just check that. And so let's look at the syllabus. And so I apologize for running a little late. Normally I'm not so behind, but I was helping with the week of welcome, and then no one showed up to relieve me, so I was nervously there. Anyways, syllabus is a little bare bones right now, but I think all the essential information is there. Blah, blah, blah. Gonna do some chemistry. Does everyone have a textbook? So I will say, oh, that's...
Yeah, like I was trying to, yeah.
Well, so much for that.
I was trying to find a syllabus and it wouldn't even populate, like it didn't populate until today.
Yeah, well, that's my fault, because I didn't make the syllabus till last night, so.
Oh, no, none of my classes, they were redoing Blackboard, so you couldn't find your stuff.
Oh, weird. Okay, well, that's unfortunate, because there is a textbook, and it should have been there. But I was going to say, if you didn't purchase your textbook yet, or you have financial hardships, especially if you're just taking Chem 104, so just an FYI, Chem 104 is part of this Chem 100 level series of Chem 105, so Chem 104, Chem 105, Chem 106. But most people don't go on to Chem 105 and Chem 106. And truth be told, like, I can't say they're the most useful course unless you just want a survey of organic chemistry and biochemistry. And so I encourage people, if you're not going to go on to 105, 106, you can go to OpenStax, and usually I just search OpenStax chemistry. You can go to OpenStax, and then you go to chemistry. And the Adams First edition is going to line up better. And it, doesn't match your textbook perfectly, but this is just intro, general chemistry, pretty basic. And so you can find this information kind of anywhere. So this is a really good resource, this OpenStax textbook. And it kind of goes through the same things we'll be doing, intro to measurements, properties, all those good things. So this is an excellent resource. If you haven't bought your textbook, didn't know there was a textbook, this is completely free online. So that is available. Post that in the notes. And so another thing you notice, how I run my class. Let's open up another Blackboard. They updated Blackboard, and I don't notice any difference except it's worse. Because my favorite thing to do is like right-click on all my courses and open up a million tabs. Now you can't right-click. It's the one feature.
Fine.
Yeah, that was like the one feature I used.
Yeah,
but
I use it too.
yeah. Anyways, I don't know what they updated about Blackboard. But what I tried to do for y'all is, I didn't label my syllabus yet, but I have this chapter 1 up, so I'll separate it by chapters. And I'll print out the homework in a second here once we have a break. But I post our lecture notes there, and I always use them in this OneNote format. And so that's what I use, so you can write in there. So some people like this if you have OneNote. And note you have to have like the full desktop version for the files that I use, because there's two different versions of OneNote. There's like the more pared down like app version versus a full version. And so if you have explored my shell, you may have seen that. Otherwise, I also post the notes as PDF. And then at the end of the chapter, I'll try to post the completed notes with all my annotations and markings. So blah, blah, blah. So you see, like I said, I'll print out the homework for you. And then we'll have our lab 1 this week. So let's go back to the syllabus. So yeah, I'm pretty lenient on like late work and stuff, but this is an 8-week class. It's gonna fly by quickly, so just try to keep up with all your work. And then chemistry, I know it's hard, especially, how many of you have taken any chemistry before? Okay, so like half, yeah, and that's perfectly fine. So, and chemistry is like learning a new language, so if you get totally stuck, which can happen to people, you just get stuck, you freak out, there's all these symbols and numbers floating around. That's fine, don't worry about the due dates, just come get help from me. I'd much rather we work through it than you're stressing about due dates and stuff. So there's our general weighting. So exams are 50%, lab reports 20%. We'll have a lab practicum that's 10%, and then homework quizzes. And so the way homeworks work is homeworks are just completion grades, so I don't check them or look at them. And then answers are posted in the content page, so they're down at the bottom here as a study guide. And so let's go back at the syllabus. And so this is our schedule, so probably the most important part of the syllabus. And so I just go through what lectures we're doing. So this first week, we'll start on chapter 1, and then we're doing labs 1 and 2 in class, so I'll try to print those out for recitation today. And then next week, chapter 2 and 3. And so notice we'll have a quiz every Monday, so obviously we won't have one today. We might do just like a really small get-to-know-you quiz. And so that'll be kind of the general pattern, is you'll learn something, quiz on it the following week, and that quiz will always take place in recitation. And so you notice recitation, right, is scheduled right after this class, so we'll take a little break. And then recitations are time to quiz and then do homework, ask questions. It's more kind of a free-for-all study period. And then your homeworks will also be typically due on Monday. And then labs, I just kind of ask that you turn them in like a week after we do them roughly. And again, same thing with labs. If you need a little more time, that's fine. I'm not going to bust you with the due dates. Just get help and get it turned in. And so you can see these weeks will fly by. And so put it on your calendar. We have exam 1 scheduled for that Monday, July 31st. So that'll be over the first 4 chapters. Then we'll continue on with chapter 5 and all our labs. So pretty typical schedule. You can see quizzes again every Monday. And then that brings us to our final week, week 8. So we'll do a little review on that Monday, quiz during recitation, and then we'll have our exam on that day, and then also a lab practicum. And all that is like I'll have some basic lab skill that you should have done before, maybe like weighing something, calculating density, something simple, and then maybe some multiple choice questions just to make sure you've been following along. So this shouldn't be too difficult. I don't want anyone to stress about the lab practicum, and you'll be able to use your notes for that. And it's the same thing, all my tests and quizzes are open note. So they're open everything. Yeah, I mean, you know, real world chemists, you're gonna have your resources to look up stuff. I just care about, you know, can you apply things, can you plug in formulas, all that good stuff. All right, blah, blah, blah. And so the other thing that I do for y'all, and I will post a link to it later, I just didn't want to post it now, is so right now, why it takes so long to set up is because I like to live stream the lectures to YouTube, so in case you can't make it that day, you're sick, you can follow along online. You have a chat too that I can see what you are doing and typing, so you can chat to me. But then it's also available asynchronously to watch later. A lot of students told me that they were like rewatching the lectures, which I initially found kind of strange, but you know, if you all like that, I will make that resource available. So I'll post an announcement with the link to the YouTube, but I just say, you know, don't become dependent on the YouTube instead of going to class. You know, you should come to class as long as you are physically able to. You know, I understand kids happen, life happens, all that, but so I have that as a resource, but just don't be dependent on it. All right, have I covered everything? Do we have any questions?
So I just double checked the bookstore, something popped up, and nothing's still there.
I have a question. When you pull up, is it just popping up the recitation lab? Or is it only?
Yeah, it's just the lab recitation.
So if you go to the top right corner and hit search, I had to do this too. You'll actually type in introductory chemistry, and it'll do the CHEM 104 -02, and then the book will pop up. But for some reason, it's just not self-populating the class for people who are veteran. It's only doing the recitation lab, which don't have books.
Yeah.
Oh, okay.
But although it doesn't have a title or a author, is that normal?
No,
At
I
least
got
in the
to.
bookstore.
It's supposed to be
It just says, Chem 104, intro to Chem 1.
So the book we use is this one, and I can also make an announcement. I think we're technically using like the second edition, so the edition doesn't matter. Like buy the cheapest edition, essentially, because I'm never going to assign you book problems. Yeah, that's also the book. So what's weird? Yeah, so that's they have custom print copies for RCC that they do. So that might be why the book name is strange when you look it up on Ambassador.
It's like a hybrid book. I only found it one place, like on
Yeah, but because it's a special print,
Yeah.
like, it's super annoying how we've done things.
That's the one it's popping up, because it literally just says Chem 104 Intro to Chem, which is like the
Yeah, but what it is it's this book, so it's general organic and biological chemistry, but it looks like the 4th edition might be cheaper, if you can get it cheap.
The one I found when I searched it up was introductory chemistry. Is that it, or?
That's the one, that one right there. Yeah, that's the class, but the actual book populates that
Okay.
quickly.
Yeah, 'cause it didn't even pull the class for me. And I registered it. Yep, here it is now.
So yeah, this is a book, if you would like to take the whole year, I would recommend buying the book. Otherwise, the bookstore is gonna be confusing and like try to sell you it as 3 separate like textbooks. I don't understand it. All right, are we okay with the textbook?
Yeah, we are.
All right.
It turns out it didn't select the actual class. It only selected like the resuscitation and the lab.
Yeah, no, I apologize for all these like small little, I don't even know what you call them, bureaucratic things. Anyways, I won't go on a rant. Let's talk about chemistry. So what is chemistry? And I'll admit, I'm slightly biased as a chemist myself, but chemist, I think, is part of the central science to a lot of different fields. So we have, chemistry is obviously related to nuclear chemistry, how we can make power, related to, chemical engineering, materials, nanoscience. Now they're getting into like drug delivery with nanotechnology, also really important in materials. You can go into environmental chemistry, which is obviously wide and broad. And of course, it relates to biology, medicine. Medicine's, of course, huge with drug development. I'm going to put just a bunch of money signs there. And of course, ag is also big money for chemists, so I'll just put more money signs everywhere. So ag, fertilizer, any sort of nitrogen fixation or different sources of nitrogen for fertilizers, that's huge. And then of course you can relate that to geochemistry, anything from, what's a rock made of to how we date things and all that fun stuff. And of course it's related to physics, chemical physics, and you have math and computer science over here. And of course you can do like computational chemistry, and math is of course fundamental. So what are all y'all's interests in? Let's start. Adar, what's your interest? What's your major or field of study or whatever?
Emerging media digital arts course right now.
Okay, so we got art. Where can we put that? I'm going to put art is totally related to chemistry. We got colors and pigments. There's a lot of cool historical stuff. There was like an article recently about, our local Southern Oregon Historical Society, and they were testing the materials, and they were finding that a lot of them were actually toxic because, they used obviously toxic materials back in the day to make garments, or ended up in there. Remind me your name again.
Josh.
Josh. All right, Josh, what's your field of interest?
Computer sciences.
So computer science, what are you thinking about doing with that?
So I'm doing cybersecurity and software engineering.
Nice. Cybersecurity. I'm sure that's still related to chemistry ultimately. All the computing that goes into that technology, materials, and also learning to problem solve. And then are you Alicia?
Yeah.
All right, what's your area of interest?
Nursing.
So nursing, that's of course hugely related to chemistry. And since you're going to be a future nurse too, you got to make sure you watch your units and all that. That's always super important. Milligrams, micrograms. All right, what else do we have? Are you Emma? Okay, Emma, what's your area of interest? Dental hygiene, awesome. So put that with medicine. Again, all related, either materials, like what chemicals too, right? How do you strengthen teeth? How do you make fillers? All that things related to dental hygiene. And you probably also want to know your units as well. And Trey, what's your area of interest?
Not entirely sure yet, but like, more like in the writing field. So it's great to know how chemicals work, especially for like any like sort of like, I guess, crime novel or something like that.
I like your crime novel.
Better than Googling it, so.
Yeah, we could go on. Did you ever watch that Netflix special about like the crime labs that there are issues with because people are getting testing the substances in other ways? We'll see before they put them in the.
Oh, I have not.
Yeah, that was. I can't remember the name of the documentary, but a bunch of cases had to be thrown out because the lab techs were like testing all the drugs, were doing the drugs, and then yeah.
That might make the workplace more interesting.
Gotta make sure it was all filtered.
Yeah.
It's the pure stuff.
And then Kylie, what's your area of interest?
Ultrasound imaging technology.
Ultrasound imaging. Feel like you got more physics going on with the ultrasound, but chemistry, of course, super important with medicine. Man, that's awesome. Y'all are all over the place. So that'll be fun, and I look forward to hearing everyone's perspective in this class. You know, that's part of what chemistry is for, and how can we combine all our different ideas to work with this fundamental science. And so let's further define what chemistry is. And so chemistry is the study of matter, and of course you know matter is everything and everywhere. And so matter is anything that has mass and takes up space. So that can be right the air, the desk, anything, your water that you're drinking. And matter can also change from one form to the other. And so we'll look at chemical changes where substances are used up and others can be formed in their place. And I'm sure you've seen this, you know, burning is the first example that everyone thinks of. So burning propane, or maybe baking a cake or something, all those are chemical changes.
Creation of salt, that count? The two different elements combining to make table salt?
Yeah, so if you took like sodium, chlorine, and did that horrible, nasty reaction. But yeah, you would make table salt, so that'd be a good chemical change. And then in physical changes, matter does not lose its identity, so it just changes states. And of course, quick example, everyone's probably seen water in all three states, so solid as ice, liquid as you're drinking, everyone's drinking water. And of course, you see it boil to become steam. So we'll look at that. All right, so let's look at our states of matter. Probably a bit of review. So matter can be classified according to its state. So solid, liquid, gas, so we're just focusing on our three basic states. And so if we zoom in a little bit, we can get down to the molecular level. So in a solid state, we have particles are tightly packed and fixed into place. And I usually say defined volume and shape. And so you guys are pretty well aware of that. So your table, right, isn't going to go anywhere. It's not going to change shape. And we can see our atoms, right, are very tightly packed together, so they're not moving. And of course, they still have vibrational movement, so we're not looking at that right now. There's still movement of the electrons floating around, so they're not completely still vibrating at least, but they just can't slide past one another. And so as we increase the energy then, and then we get to the liquid state, so now we have our state where the particles are still closely packed together, but now they're not so tightly packed, and they can now slide past one another, and of course take the shape of the container. And And so now we can say defined volume for our liquid, but not defined shape. And so, of course, you've seen that. You can pour water into a bunch of different containers, and it'll take the shape of that container. And then as we give it even more energy, so now our particles are spaced widely apart. Now we're in the gaseous state. So what's the term that people use for gases sometimes? It's like a certain term. It's kind of related to this volume shape business. What's the difference with gases, though?
Show in the dark. Transparent?
It was a good guess, but liquids are transparent, so it can't be that.
Oh, yeah, true.
What else? What can you do to gases, though, that you can't do to solids and liquids? And think about how they're stored. Gases are stored. Compress. Got it. So they are compressible. And
It took me that whole time to think about it.
no, it was a very vague question. So. But yeah, that is the main difference. And of course, if they're compressible, that means that they have no defined volume or shape. So they can obviously take the shape of any container. You can compress them down, and you might be familiar with like those huge liquid nitrogen tanks that they fill up your tires with air. And so liquid nitrogen is really cool, right? You have this huge tank, and they compress it all the way down until it's a liquid. So now we compressed it to its liquid form. And then you have your pressurized valve, open it back up, and then it opens up to a gas form. And then, of course, can fill up your tire or a balloon, whatever else. Excellent. So recap, so like we said, our solid matter, they just have vibrational movement, but they can't slide past. And of course we can think of solids, so ice, aluminum, diamond, all those are good examples, and I'm sure you guys could go on and on with more examples. And then liquids, like we said, fixed volume, not a fixed shape. And of course some substances, water, alcohol, both ones you would consume and ones you could use for other methods. So rubbing alcohol or other alcohols are good. You could also combust alcohols. So gasoline is mainly octanol or octane. And so those are all substances that are liquids. And again, you can certainly think of more. And so gas, they are free to move relative to one another, a lot of space between them. And of course, we came up with that term compressible. And so just a little visual. So of course, right, you have a mass of solid, let's say sodium chloride or whatever, and you could try to compress it, wouldn't go anywhere. But then you have your gas, so this looks like CO2 drawn here. And so CO2, right, we could compress it, and of course compress it all the way to dry ice if you wanted. Questions so far?
Is it possible to like compress a gas like too much and then wouldn't that create a reaction?
I think you would have to have more like a mixture of two gases for that. And
That makes more sense.
yeah, I mean, I'm sure we'll talk about this later, but like the main thing that comes to mind is the Haber-Bosch process. And I'll talk about this probably like a million times. But yeah, if you just had a gas and compressed it, it would just go to maybe a solid form if it can. But what you can do is, so this is the Haber-Bosch reaction. Oops. And let me balance that. All right, so now we have a balanced equation. And let's write what this is. So And so as you can tell by this reaction, you take nitrogen and some hydrogen. So nitrogen from the atmosphere, hydrogen I think usually comes from what's it called? Fossil fuel mining process or combustion, refining. But if you combine these two, and so the key point with this Haber-Bosch process is it's kind of difficult to accomplish, but it takes place at high temperatures and high pressures. And so in industry, that's something that they have to balance is, yes, compressing them, putting them at high pressures so that they do react to create ammonia. So that would be what you're thinking of. And I don't know how much we'll touch on it in this course, but yeah, that's kind of the idea with how to make reactions go sometimes is you pressurize the system, and then that forces a reaction to happen. And so this process is super energy intensive, just FYI. So that's why there's a lot of money in ag and everything. So people, of course, you want to make ammonia because it's fertilizer, right? Increased crop yield, and all that's just money right there. All right, back to chemistry. And so something that you want to be able to do is classify matter by its components. And that's part of chemistry, is breaking some compound down. Can we get it into its elemental form? That was a lot of early chemistry, is even identifying, what the heck are these gases that are floating around? Even identifying that there was gas was difficult. And so we have a little flow chart here. So you start with kind of matter, and then you have to ask yourself, is it one type of particle or not? And so it might be easier. So let's kind of go through our scenarios. And so if it's one type of particle, then you have to ask, is it a pure substance, or is it, so basically, is it an element, or is it a compound? Let me see where I put. And so looking at our elements, so there's our periodic table of elements, and I need to print y'all periodic tables, and I apologize for not being super prepared. But right, anything here is going to be an atom, so these are fundamental elements that can combine to make compounds. And so going back here to our pure substance, right, if it's an element, it's just going to be containing one type of atom, and that atom again would have to be located somewhere on the periodic table. So of course we have oxygen, carbon. If you're just having a pile of carbon, that would be considered an element. And then so a compound, let's define it as anything with a defined chemical formula. And so what might be some examples then of compounds? So water. What else? Yeah, it can be any. Yeah, so it could be solid, liquid, gas, other, salt, so NaCl, sugar, those are all good ones.
Would yeast be one? Or would it create
I think yeast would be more like a organism. Yeah, it's more in the fungi category, so we'll leave it out of our matter. Other ideas? Acetic acid, yeah. What's the common name for that one? Do you know the common name?
Vinegar?
Yeah. Yeah.
Does
So,
hydrochloric acid count?
oh yeah. Yeah, you guys know your compounds. Saline would be more of a mixture now. So let's look at saline and let's classify that. So now we have, so saline, so what's saline made out of?
Salt?
Yeah, salt and,
Water?
yep. So if it's salt and water, then that means it's two types of particles.
Water's compound.
Yeah,
Adding salt to it, so it's.
yeah, it gets tricky. So then it's a mixture, right? But then you have to ask yourself, so is it uniform throughout? And that just means, I just say, is the first bite the same as the last? And we can go through examples of that. So is saline heterogeneous or homogeneous?
The same amounts in each.
Or just like, so if you have a solution of saline, oh, if it's homogeneous, that just means that you have like the same constant.
It'd be heterogeneous, isn't it?
No, it'd be homogeneous.
Okay.
So I think you're thinking of like different amounts of saline. So you can make different amounts of it, but just that solution
It's
that
always
you've
the
made,
same
yeah.
mixture of stuff.
Yeah, because heterogeneous would mean, like, let's say you had a saline solution, but you didn't make it properly, and there are like giant crystals at the bottom, which would obviously be horrible for your patient. But that's what it means by heterogeneous, where it's like you can see there's a difference in the composition. So I'll put hetero, so if you had, right, a bunch of H2O and salt chunks, or, a good example, and they have it here, of the heterogeneous is like wet sand. You take it from the beach and the top layer is kind of clear, the bottom's really murky. So that's going to be heterogeneous, but your saline solution, at least of course if you prepare it properly, should be totally homogeneous throughout. So does that kind of make sense? And we can identify our compounds that were in there, so H2O and salt, to make our saline solution. So with compounds, I'll just add, don't forget like drugs, but then also be careful because like some drugs are not pure compounds, so it depends, like, right, aspirin, for example, is a pure compound, but then the pill itself may not be, so it could have like aspirin and, or like, multiple compounds in there, or sugar, whatever fillers, so that's kind of.
So is a compound only two elements put together, or can it be three, like?
It can be multiple, so it could be, yeah. I'll just pull up. I just picked, right, fluoxetine, so that's Prozac. So that would be another drug or pure compound. Where's the Wikipedia page? This is what I'm looking for. So, right, the compound itself, it has a lot of elements in there now. So it has a formula. So it has carbons, hydrogens, fluorines, nitrogen, oxygen. But the important thing is just to find chemical formula. And so same thing, like caffeine would be a compound, but then coffee is your homogeneous mixture, right, with your caffeine and your tannins for flavor and sugar. So I'll put caffeine here. But then for homogeneous, I'll do coffee. And of course, right, it can have all sorts of molecules in there, or flavor molecules, sugar, etc. And then maybe, I don't see anyone with a heterogeneous coffee mixture, but at least one of my favorite coffee drinks, if I feel like going crazy, is like a Java chip frappuccino, right? And so that's going to be heterogeneous if it has, giant chunks of chocolate chips in there. So it's not uniform throughout is what you're going for. So same thing, we want to start thinking about food and get really hungry. So like cookie dough ice cream. That would be a heterogeneous mixture, right? Again, you got the chunks of cookie, and then maybe you'll eat another bite that's just plain vanilla. And so that's heterogeneous versus, just like a simple vanilla bean or chocolate ice cream, where again, it's just that same flavor throughout, right? Your vanilla bean is going to be the same with your first bite and your last bite versus your cookie, which, your first bite may be a huge cookie, and then down at the end, there's nothing left but just your base ice cream. Other examples of heterogeneous mixtures.
Scroll back out for just a second.
Couldn't that just be like a dissolved sugar?
Yep, so it could be, yeah. So we could say super saturated sugar, where there's a clump at the bottom. That would be a perfect example. And then I'll put, right, like a simple syrup, though. That would be your homogeneous mixture with that nice uniform sugar throughout. Other examples for either one of these? What?
We're trying to get the names right.
Oh, yeah.
Would like gasoline be a compound, but diesel be a homogeneous mixture?
I think they would both be.
Because diesel is taking the regular gasoline, making it pure form and adding extra oils.
Yeah, but it should still be a mixture of like a bunch of different like hydrocarbons. So I think they're both.
Compounds, just different makeups. Okay.
Yeah. So they're all like heavy hydrocarbons. So regular fuel is like your lighter hydrocarbons, so it tends to be more octane. But there's other size hydrocarbons, and sometimes ethanol is added. And then the diesel is going to be like your heavier burning ones. So yeah, those would all be homogeneous mixtures, probably for gasoline and diesel fuel.
What about like a painting for heterogeneous?
I like it. That's a different one. So like paint. So like a painting, like a finished product. Yeah, so I'll put that there. A finished like painting. Yeah, with different colors versus like a paint, we'll say.
So does that mean like it's you can still like well metaphorically you can still separate the two stuff that makes it? That makes sense?
Yeah,
Like
so
cookie dough ice cream, like you can separate the cookie dough and the ice cream. But if it's homogeneous, that means like they're like compounded together to
well, you still might be able to separate it.
Oh, okay.
Yeah, so anything that's a mixture, so either heterogeneous or homogeneous, the goal of chemists would then be to like separate it. Yeah. But yeah, you're right, with like a heterogeneous mixture, you might be able to use different techniques, like more physical sifting, but that's, an entire chemist's life can be just like how to purify stuff. I once had a mentor who said like, my kid could mix stuff together, but the real thing is in being able to purify something and get a nice finished product. All right, let's move on, and we can always come back to this. So this is just going over the text of it. So again, heterogeneous mixtures have your variable composition, while homogeneous, like we went over again, it's two made up of multiple substances. I'll kind of put in there compounds, like you're recognizing. So it's made up of two or more compounds. It appears to be one substance, so same thing throughout. And so like I mentioned, a big part of chemistry is purification. And so this is just showing kind of the most common techniques for for purifying substances. So that's going to be a distillation. And so you would not use an open flame, by the way, but you would instead have some other heating source. So now you use what are called heating mantles. And it's just this electric thing that cups around your flask and heats with a thermocouple. You would never want to use an open source because that's obviously a good way to start a fire. So if you're distilling something, especially an organic, and you have this little joint here in your glass where if you had, some vapor escape with your open source, there goes your whole apparatus up in flames.
That was my high school. We had like open flames and gas leaks at the same time. Like you could smell the gas in the room.
Yeah.
Yeah, it was. I
Yeah.
don't know how the hell they didn't get shut down.
Well, open flames themselves aren't terrible. It's when they're combined with distillation. So you shouldn't. Yeah, it depends what you're doing.
The flames didn't even work though too, so I guess we're safe.
Yeah, I don't know if you're safe if you're breathing gas.
It's better than being burned alive, so at least I think it is.
So the basic idea, so let's say you're stranded on a desert island. You have a bunch of salt water around, and then you could, of course, heat it. So then your water goes up, leaving the salt behind. And then you have here what's called a condenser. And so it's hard to tell with this simple illustration, but it's a jacketed condenser, so the inside does not ever come into contact with water. That just provides a tunnel for your whatever liquid you're distilling to travel through, and then the water goes outside of the jacket to cool it down, and then you have your receiving flask with your pure substance. So you can distill, if you wanted to separate out like your ethanol, like your alcohol mixtures, go through distillation process to get them, more and more pure. You can separate, like I mentioned, water from salt, or just any two different boiling substances. You might be able to separate them out with a distillation, or anything with solids. You can leave solids behind. Okay, questions so far?
So, just a quick question. Are we like reading over like chapter 1 and homework 2 as well, or is it just like lecture only, or is it like lecture and read?
Oh, yeah, you're expected to keep up with reading the chapter. So whatever that looks like for you. Some people like reading beforehand, so they feel like they're reviewing, or maybe you want to listen to the lecture and then read the chapter. But that's all up to you. And of course, I don't require you to read the chapter, but I would highly recommend reading.
Oh yeah, just want to double check.
But I try to give you everything you need in class. So now we'll start getting into units. And so let's ask ourselves, well, why do units even matter? And so this was a pretty big oopsie. And so we have here a Boeing Delta II expendable launch vehicle lifted off with NASA's Mars Climate Orbiter. And so the NASA Review Board found that there was a problem in the software controlling the orbiter's thrusters. And so what happened is that the software was calculating the force in pounds, so it was in our American units. But then the next piece of coding that was used was in the metric unit, so it was doing newtons per square meter, so they're not in the same units. And so this was due to the two different groups using different units. So Lockheed Martin was again using pounds, and NASA engineer was using metric units, and they assumed that the conversion had been made. It was not, and so what happened was the spacecraft ended up too close to the planet's atmosphere, and it just ended up burning and breaking up into a million pieces. And so that was obviously a very expensive mistake. And so that's why, units matter. Double check your units. Anytime you're giving an answer to me, write the units so I know. So really important. And so let's talk about everything. So science obviously covers a wide range of things. So we look at human hair to the size of atoms, elephants, distance to stars. And so let's see if we can guess. So what is the scale of the human hair? Like what?
Per strand?
Yeah, so how big is one strand of human hair? Like the units it might be on. Very small.
Not as small as that. So, well, it depends what you're saying.
Do you know like what size, like on meters or millimeters, micrometers? Yeah, micro. So it's about like 1 micrometer. So that's 1 times 10 to the negative 6 meters. What about the size of an atom? Do you know what scale that's usually on? Yeah, nanometers. So they're about nanometers. And so a nanometer is 1 times 10 to the negative 9 meters. And sometimes in chemistry you'll see this other one called the angstrom, and that's 1 times 10 to the negative 10 meters. Excellent. What about an elephant? How big is an elephant? Tons. So I think they're about 1 to 2 tons. So anybody know how many kilograms that is? Yeah, so about 2,000 kilograms roughly. So I think like 1 ton is just under 1,000 kilograms. And then what about distance to the nearest star? Light years. So I think it's 4.35 light years roughly.
Better answer than miles. That's a better answer than miles.
I'm going to get you a kilometer. And so how many kilometers that is 4.11 times 10 to the 13 kilometers. That's pretty wild. Let's get it in miles, just for fun. So 2.55 times 10 to the 13 miles, so pretty far. And so what do we do with all this? How do we handle the tiny, the large? And so with that, we have our metric system, and we can have our prefixes. So let's look at our metric system. Oops. So of course the metric system is a little nicer than the American system just because we have our base units, and then our metric system is based on multiples of 10, so it's fairly easy. And then down here are some examples of some base units. I can zoom in a little bit more. And so later we'll talk about moles. So of course chemists use moles to define quantity. But when we look at length, so your base unit is meters, and then we'll add our prefixes. There's our meter. Mass is always in grams, so again, grams is your base unit. Volume is in liters. And then temperature is usually in Celsius, but we'll see other times where you'll want it to be in Kelvin. And then of course we have seconds, and then information, which we don't usually talk too much in this class, but that would be bytes. And so then we have our multiples of 10 are created by adding a prefix to each base unit. And so this, let's see. And so you'll want to be able to set up what's called a conversion factor. And so all a conversion factor is, it's a way to express a relationship, and it expresses the same value in different units on the top and on the bottom. And so, for example, 1 meter is equal to 1,000 millimeters. And then you can express this either way. So you can have, right, 1,000 millimeters is equal to 1 meter on bottom, or we can flip that relationship, right, and it means the same thing. There's 1 meter is equal to 1,000 millimeters. So same thing with our regular units that we're used to, right, 1 foot is equal to 12 inches. You can write that, or 12 inches is equal to 1 foot. And so the point is, eventually, right, we'll be going from one unit to the next, but you want to use your conversion factors to kind of help you decide which one to use when we're converting, and then of course, keeping it straight gives you all the right answers. And so these fractions, right, are called conversion factors because they allow us to convert. And it's a pretty basic concept that you want to get down, because you could see conversion factors for kind of anything, right? You can make things up, but the point is, can you set up these ratios, and then do you know how to use them? It'll make more sense as we do. Example. And so I like this chart better. So if we go back to these notes, so this to me is kind of confusing the way it's written, but that's just my brain. So let's look at the difference. And so this says quantity in 1 base unit. So that means it's comparing this to the base unit. And so if we look at tera, that means that 1 times 10 to the negative 12 tera, and let's just say teragrams, we'll just use grams for fun, is equal to 1 gram. And that's kind of confusing to me. I don't like the little negative units. To me, it makes more sense the way I have this chart set up. And so this multiplier, this is times your base unit. And it all means the same thing. But what this is saying, times the base unit, is it's going to be, right, 1 times 10 to the 12 grams is equal to 1 teragram. So does that make sense how they're both saying the same thing, but kind of in different ways? And so I'll write out all our conversion factors. And I think I'm going to try to print this out right now. What am I doing? Oops. Come on. What's annoying is I can't print from this computer, so I got to send it to another computer. But what we're saying, so now I'll write out everything we're saying. So we could do, again, 1 teragram is equal to 1 times 10 to the 12 grams, or 1 times 10 to the negative 12 teragrams is equal to 1 gram. And then, of course, we can write it upside down or flip it, All right, let me go print this page.
Does tera always mean grams, or it could be different units of measurement?
Oh, yeah, it could be anything, so, right, terameters, you know, watts, bytes. So you can add this tera to anything. I just put grams there to help focus. All right, give me 1 second, I'll be right back. So yeah, practice writing these conversion factors. And also, can you tell that all you have to do to get from one of the others, you can multiply by 10 to the 12th, right? So if we're starting here, you want to get to that one. 1 times 10 to the 12th, 1 times 10 to the 12th. So essentially, multiplying by 1, right, gets us to that other one. And then, so just practice, right, writing it the other way, too. So 1 gram is equal to 1 times 10 to the negative 12 teragrams. Or 1 times 10 to the 12 grams is equal to 1 teragram. Oops. And then let's look at some of the negative ones. So I'll give you some time to go through them right now. But then, so again, looking at this, so this is times the base unit. So that means, right, 1 times 10 to the negative 9, let's just go with meters, is equal to 1 nanometer. And then you can go the other way, so 1 times 10 to the 9 nanometers then will be equal to 1 meter. And of course you could write that the other way, just flipping them.
It's positive exponent, right, on the bottom there?
Yes, this one is positive. And so me personally, and you know, you can do this on your sheet, I can print out some more copies. I like to just get everything in positive exponents if I can. It's just, you know, easier for my brain if I'm doing mental math especially. But obviously you're more than welcome to do whatever makes the most sense for you.
It's a good question about, so I noticed that on the second equation, actually, never mind. So why is the formula the nanometers instead of the one? Like the one's the meter, and then the formula is the nanometers. In the first equation, it's switched on the bottom, on the when we just saw. Yeah, that one.
Sorry, repeat the question.
So, because I'm just trying to formulate the question. So, what I noticed is that the one and the formula got swapped when it came to units. When they swapped places, is that like? I can't really describe it.
Are you talking about that meters is on
Yeah.
top
meters on
here,
top.
or?
Yeah.
Because it also, it doesn't matter like which one's necessarily on top when we're just writing our conversion factors, right? Because right now we're just practicing. So you could write, you know, 1 nanometer.
Variables on top, like nanometers and meters.
Not when we're just writing it out.
Okay.
Yeah. And so let's maybe do a practice so you can see kind of where we're going with this.
How about that nanometer? Were we supposed to keep the negative 9 or were we supposed to do something else?
So which one? And it doesn't matter, right? Because you can write 4 total conversion factors, 2 of them with negatives and 2 without. And really you only need 2, but the negatives are just kind of in there as extra.
So they need positive as well? Negative 9. Or any negative number at that point?
So we have, all right, 2 different ways of saying it. So we could say, right, 1 meter is equal to 1 times 10 to the negative 9 nanometers. And so nanometers, again, this is by the base units. Nanometers are teeny tiny. So we need a lot of them to make it 1 meter. And then this is just saying kind of the same thing. So we could use our positive exponents, right? You can write it flip, doesn't matter. 1 times 10 to the 9th nanometers is equal to 1 meter. So these can be what I would say like one set of conversion factors. But then if you like the negative ones, this is your second set. And so let's kind of do a practice conversion. Because this can seem confusing at first, I think, but once you do it, and so let's just say we want to convert 750 nanometers. Oh, let's not do that. Let's do 7.5 times 10 to the negative 7 meters to nanometers. And so let's do this problem together. So the first way, and I'm going to do this really step by step initially. And so I just like to put here what we're starting with. And so that's just rewriting this. So we're starting with 7.5 times 10 to the negative 7 meters. And then we know in this middle here, we're going to need some conversion factor. And then we need to end up with nanometers. So then what you do is you can find your correct conversion factor. So we're going from meters to nanometers. So we look at our little conversion factors that we have up here. And so if we want to end up with nanometers, you want to pick one of these combinations where nanometers is on the top. And so basically looking at this one, we have two different options, depending if we wrote it with our positive exponent or with our negative exponent. So both of these would work. And you can see, right, mathematically, they're the same. So let's see. Let's just try it out. So let's do the positive one. So 1 times 10 to the 9th nanometers over 1 meter. So we can plug that in. So 1 times 10 to the 9th nanometers, right, is equal to 1 meter. And then I'm just going to pull out my calculator to be really explicit. And so let's just try. So 7.5. And so if you're using one of these styles of calculators, make sure you use these E exponent buttons to do times 10. You don't want to actually type out times 10 to the whatever. We'll start screwing up. So times 10 to the negative 7th times 1 times 10 to the 9th here. And so that gives us 750 nanometers. And then let's just plug in our other conversion. So again, we'll start the same thing. I'm just proving that it doesn't matter which one you use. And so let's pick our conversion factor. Again, so it has to be one of these where nanometers on top. So we could pick this one too, where 1 nanometer is equal to 1 times 10 to the negative 9 meters. And so I'll just set that up. So 1 nanometer is equal to 1 times 10 to the negative 9 meters. And so you can already tell, right, you're dividing by a negative exponent, which really just means you're multiplying by the positive. But I'll plug it in, again, just so we can see. And now it's divided by 1 times 10 to the negative 9th. And so that also gives us 750. So does that kind of make sense how this is going to work? And so again, you may want to go through these and put them all in like positive conversion factors if that helps. You could write out all 4 if that helps you. It doesn't matter, just as long as we can get to a correct conversion factor and then understand how to use it. And of course, right, we can go through, and I didn't properly do my unit crossing, but right, meters, so that cancels out to give us nanometers. Same things, meters, cancels out, gives you nanometers. All right, so let's take maybe 5 minutes or so and kind of go through. So write out these conversion factors, get with your neighbors. And so while you do that, I think I'm going to run off some periodic table hard copies for you, and then we'll kind of go over these, and we'll do a little more unit conversion practice. conversion factors going. Did we get this for gigameters? So 1 times 10 to the 9th meters equals 1 gigameter, or 1 times 10 to the negative 9th gigameters. And I just put meters for placeholder, but right, doesn't matter. Gigagrams, gigabytes, gigaseconds equals 1 base
So
unit.
Sorry, so if it switches, sides, it turns the exponent sign negative or positive? So it's 1 times 10 to the negative 9th power, when it was originally a positive 9.
So yeah, it depends. So in this case, right, giga is large. So now we're saying like a very small portion of 1 gigameter is going to get us back to a meter.
That makes more sense. 'Cause, yeah, I just got out of doing math like 95, so like, we were told about, switching that stuff all the time, so I just got confused in how originally, a equation like that could fit into like a smaller, I guess, unit measurement. Now it makes more sense. Guys, because you're using a negative exponent.
Yeah, I mean, I like the positive exponents personally. So again, you're just thinking times the base unit. So 1 times 10 to the 6 meters then is 1 megameter. And of course, you can just flip that. Again, just times your base unit. So 1 times 10 to the 3rd meters then is 1 kilometer. And deci. So now deci is 10. So you have 10 decimeters in 1 meter. Centi, so that's 100 centimeters in 1 meter. And, oh, just some things to watch out for. So, right, you have mega is this big capital M. Meters is always just regular M. And then don't forget you have milli, which can be kind of confusing. So you have like mm for millimeters. And then not to be confused with micro. So micro is that weird, it's like a mu. It looks like a U with a big tail on it. That's micro. And so micro, so that'd be 1 times 10 to the negative 6 meters is 1 micrometer. Or 1 times 10 to the 6 micrometers is equal to 1 meter, if you like the positive values. And then femto, so femto, we hardly ever use. This is super, super fast. It was Ahmed Zewail, who I think it was 2015, 2012, won the Nobel Prize for his femto laser spectroscopy work. And unfortunately, he passed away now. Oh, I did that wrong. Sorry. So negative 15 meters equals 1 femtometer, or 1 times 10 to the 15th femtometers equals 1 meter.
Most good stuff, I'm trying to figure out like when to switch the exponents to go negative or positive or not.
That's, so I guess, like the first part is, do you want to be in negative or positive ones? Because I kind of encourage positive.
Yeah.
Because, right, they all mean the same thing. So it's just a question of, like, what makes more sense for your brain in some cases.
Okay,
And
I'm just used to like having to learn like all the methods because you get like a question on the test that asks you to do a specific method. That's what I'm used to. what I was just wondering.
Right. But then, because the point is, these all kind of mean the same thing, right? So you could use negative exponents, you can use positive. It's just setting it up properly and not kind of like mixing yourself up.
I guess it's the setting up properly I'm trouble with.
So let's do some practice problems. So we all kind of have our page filled in to help us. And so let's move on to some practice problems. So let's do this practice. So I have all these problems, but let's just look at, let's start with these first 3 initially. So see if you can set those up. So this is a small class, so if anyone wants to write it on the board too, whatever answer. I still haven't figured out a sexy way to do what I want to do, which would be to like show people's answers on like the big screen. But haven't found the missing piece of technology that would help me. Yeah. I know. I've always wanted like a hot seat computer, but I don't have that set up either. Yeah, a smart board would be awesome. They're just so expensive. Yeah, that's what I need.
I know my brother uses it at the high school.
Mm.
Ask him what it is.
Somehow I did it backwards.
What does that mean? He went from.
I ended up at 5,000 kilometers.
So try again. You got to correct. See, that's a good. I think that's a great example of like sanity check. Like you always have to do a little sanity check. Like, does this make sense? And so once you do your sanity check, check your conversion factors again, check your math.
So on the calculator, we put like 1E3, right? Or would it be 1 times E3?
Just do 1e3. Yeah, and that means times 10 to the 3rd power.
Like lowercase e, right? On the calculator,
Oh, that's the other e.
that's the exponent e.
Yeah, that's the e1. That's
Oh.
e as in 2 point whatever it is.
Oh,
Yeah,
so
so,
1 capital E3.
yeah,
Okay.
that big EE, yeah.
Okay, that makes way more sense.
I know. So yeah, I highly recommend bring whatever calculator you plan on using on the exam to class. I also have calculators that you can borrow for the exam, and if you want to borrow them during class, I can grab them so you can kind of practice, because yes, all those little things like entering E versus E make a huge difference. So that's E as a number E versus exponent E. Does someone want to put the 5 meters to kilometers on the board for us? We even have markers? Yeah, we got markers. Oh, up.
Apparently it's called Kahoot.
Ah, Kahoot, okay.
So you can like sign up, make a quiz in there, and then people can sign in as guests, put their names in, and then they submit their answers, and it pops up on the board with their answers.
Okay, we may have to try that out in our class. I'll just see. Is that marker functioning?
That sounds about right.
Alright, one more time.
There's one more marker underneath the.
Okay.
And
All right, class. It's not taking over now. My experience, none. Apologize for my shitty handwriting. Runs my family. Oh, thank you. You want to write the answer or how I did it?
Yeah, show the work.
Okay. Maybe backwards.
I'm a little confused on your work.
So I took this function and I replaced the 1 with the 5. I solved that. I got 1,000 and then I divided it by 1,000 to get that answer.
Oh, okay, so you just, I see it, so you just did your work, okay. I got you. So I'll just write it out a little differently. So I'm just
Yeah.
starting off with the 5 meters, and then, so we have, so let's see, so you wrote your conversion factor is 1 kilometer. So I'm just gonna write this off to the side for a second. So 1 kilometer is 1 times 10 to the 3rd meters. So that looks good. And so yeah, you kind of did the work all squish, which was fine. And so I'm just going to write it out more explicitly. So 1 kilometer is 1 times 10 to the 3rd meters, which is how you knew how to divide. And so units cancel, leaving us with kilometers. And so exactly, so 0.005 kilometers. All right, did we do the next one? Who's ready for that one?
Would you traditionally solve one side of parentheses first and times it by 5 over 1, or does it matter?
It doesn't matter. So this is just a conversion factor. So you could just multiply like across or solve the division.
Okay.
So in algebra forms, all you're doing is you're timing it by 1, and then converting whatever they are. Oh my goodness, my brain's not working. Right, that's pretty much how it is. All you're doing is timing it by 1 and then converting the out or the.
Or yeah, you're just doing the division
Yeah.
too, essentially. Yeah, because you're just. It'll get more complicated later, But like you'll have, you know, multiple units. So later, right, chemistry is all about moles. So we'll be going from like grams to moles to ratios to blah. So I'm setting it up like all very explicitly so you can see your units canceling. And then, yeah, you're just either multiplying everything across on top and then dividing it by everything on bottom. Does anyone want to put this on the board for us? Yeah, go for it. I think, yeah, Josh is doing this one. If we had enough markers, I would put you. And then, Emma, do you want to do the 7 meters to centimeters conversion one? Once he finishes, or?
Are milligrams less than a gram or above a gram?
They are less than.
Less than a gram.
Yeah, so you can either go back to this, so milli, right, it's 1 times 10 to the negative third times your base unit.
So I'm just asking, for this example, why is it one, that actually is called, I'm spacing what it is. So why is it 1 m over a thousand milliems, I guess?
Oh, why is it this one?
Yeah, like wouldn't that be like a negative number, or am I just?
Well, so if you do that division, that would give you, right, a negative number. And so it's saying, right, times the base unit. So that's what we're saying, is these millimeters are really tiny. So another way, right, again, this is times the base unit. So to think about it in negative exponents, right, 1 meter then, oh my gosh, what did I write? 1 meter is equal, or excuse me, 1 times 10 to the negative third meters is equal to 1 millimeter, right?
Yeah.
So that would be one way to write it with the negative exponents. And then if you want to take it to the positive ones, you can also just multiply by 1 times 10 to the third on bottom and on top. So that's one way to mathematically do it. Does that help? Oops.
There's a big few that I tried using the 1 m over the 1,000 milliamps, because I spaced when that is called. And when I based it off that, I got like, I guess the answer for m, not milliamps. For that, when I based it off the 1 m over 1,000.
For this problem?
Yeah.
So let's go through this one. So I didn't see the answer yet. So 3 grams. And then which conversion factor did you use, you
The
said?
one on the right, the one you underlined.
This one?
Yeah, that one. 'Cause I based off like a positive value.
So the problem with this one, so which unit is on top if you use this one?
It would be grams on top.
But and then what is your final unit though?
Milligrams. So you have to base it off which.
Yeah,
is
which
on
unit
top.
is
Oh,
on
okay.
top? Yeah, so this one, you'd want to use this one, but you flip it, so then it's essentially right that
Okay,
one.
yeah.
So let's see what's on the board.
You need to cross out, and they need to be in opposite part, or one needs to be in the numerator, one needs to be in the denominator, get rid of that.
Yeah, so it looks like it's written correctly on the board here. So we have our conversion factor, so 1 times 10 to the third milligrams is equal to 1 gram, right? So that's what we have written there, so that's just our conversion factor. And so you see, right, we can get that same conversion factor from our table. And then notice, right, your units cancels, so grams cancels out, leaving us with milligrams. And so yes, we get 3,000 milligrams for that one. So is this one okay with everybody, this grams to milligrams? And you can use, again, our negative exponents if we wanted to, right? So we could use this conversion factor, our negative one. I'll just rewrite it, so 3 grams over 1. We wanted to use our negative exponents. So I have to think for a second. So 1 times 10 to the negative third grams is equal to 1 milligram. Right, so that would be another way to do it. Grams cancels out again. And again, same thing. And so if you do the division, so 3 divided by 1 times 10 to the third, that, oops, negative third. Oh my gosh, sorry. There we go. So then you still get, right, the 3,000. So let's see how our meters to centimeters went, and then we'll do the next one together. But let's see, so we have 7 meters, and we use, so there's 100 centimeters and 1 meter, so that looks good. So let me just copy the board, so 7 meters over 1, and so 100 centimeters and 1 meter, and that's good, right? We have centimeters on top, and so 700 centimeters. Questions about those first 3? So now let's look at this one together. And what do you notice about this one that might make it a little tricky? Yeah.
Non-standard forming measurement, so it's going from modified to unmodified.
Exactly. So how can we handle this?
I was thinking about this earlier. Could you take the first one, turn it into the base, and then from the base go to?
Exactly. I think that's excellent. So you guys are on the ball today. So that's what I would do, just like you were saying. And so I kind of call this, right, our 2-step conversion when you don't have anything related to the base unit. But yeah, y'all have the right idea. So see if you can set that up then, since you have the right idea, going from milligrams to grams to kilograms. And so you might need 2 conversion factors. Yeah.
And for this one, you would use the, because it's done in milli, it would, be the 1,000 over the 1. Right?
You'd want, if you want to go to your base unit, you want your base unit on top.
Okay.
Yeah, so then it'll have to be the
Oh, and then
1
makes sense,
over.
Yeah.
Yeah, so use your unit conversion and dimensional analysis to help you. Yeah, so you could, if you see the conversion factor, yeah, then you can just go for it. So that's the other method, is some people can just, see it, I know the factor, I can do it, that's perfectly fine. But yeah, for most people, usually myself included, I have to do the 2-step. But yeah, you can do it 1 step.
Would it still be a negative 3
For,
for, to convert the milli to the
So it depends. So you could just stick with like the positive units, so going from 1 gram over 1,000 milligrams. So then you don't need the negative one.
Okay.
Does that?
Okay, so when you swap at any time, like it changes the sign, is that correct?
So if you just swap them, because, right, you can just swap them. I don't know if that's what you mean by switching the top and the bottom.
Yeah.
But that won't change your exponent sign. What changes your exponent sign is multiplying it by 1, right? So just like I've shown here, where if you use the -1, so times the base unit, 1 times 10 to the -3rd meter is 1 millimeter. But then to change that to positive, you multiply it by 1 times 10 to the 3rd on top and bottom, right? And so that just gives you 1, and then that would give you 1 times 10 to the 3rd.
Oh, okay, so that's how you got the 1,000 over 1 and the 1 m over 1,000.
Yeah.
Oh,
So
okay.
that's one way to go back and forth with that one trick. So I'm kind of running out of time, so I don't want to go over our time. So let's kind of run through it together then. So we start off with 60 milligrams over 1. And so let's do our conversion factor. So how do we go from milligrams to grams then?
1 times 10 to the -3 kilograms, or going to positive.
So what's my conversion factor though? Like just give me the. So just what's the relationship?
1,000 over 1.
So that would be, let's see. So 1,000, but we need, so 1,000 milligrams equals 1 gram, right? Except, so we need grams on top, right?
Yeah.
So then we're going to have to flip that. So 1 gram over 1,000 milligrams. So 1 gram, 1,000 milligrams. And so now we're at grams. We don't have to do the math yet. I'm just canceling my units, right? So milligrams cancels. We're at grams. So now how do we go from grams to kilograms? So 1 kilogram is 1,000 grams. So again, that's just our conversion factor. So we've just essentially, right, selected our 2 appropriate conversion factors. Grams cancels out now. And so now we can just multiply everything on top divided by our bottom. And you can use mental math, of course. I'm just using the calculator to be explicit. And so we should end up with 6 times 10 to the -5th kilograms. And of course, you could do a 1-step conversion if you wanted to. So you could always figure out a new conversion factor. And all I mean by that is if you, and some people are really good at this mentally, and other people are not. It's not a big deal. Did you want to say something?
Oh, I was gonna, that's
Oh, yes. Yeah, so what was your conversion factor?
my conversion was 60 milligrams over 1 times 1 times 10 to the -6 kilograms over 1 microgram.
And so this, just pointing it out for everybody, would be the conversion factor. And so, again, if you can see that, that's great. So you can see, right, this is 10 to the -3rd, that's 10 to the 3rd. So that gives you a 10 to the 6th difference. And then kilograms is a bigger unit, so it has that -6. So you could also write 1 times 10 to the 6 milligrams is equal to 1 kilogram, etc. And then flip that if you need kilograms on top. All right, I think we have to end there for today because we are over time. But let's stick around for recitation really quick. So I'm going to go ahead and end this stream, though, so I'm going to stop streaming.